Hi, this is Peter with CalcBook, and today we're going to be looking at a timber beam column design, so looking at axial flexure and then combined loading of a sawn lumber piece. So just remember we are using the National Design Specification, the NDS spec, and that has the spec and the spec supplement. So the spec gives you your general design procedures, capacity equations, those sorts of things, right? So we can look at our flexure, shear, deflection, compression, and then our combined loading. Our supplement gives us our reference design values, right? So our shape properties, our design properties, different specific adjustment factors for the type of species, so those types of things. So for us today, right, we're going to be looking at flexure, compression, and then combined loading of those two items. Similar to sort of steel design, but NDS has their own set of equations for that combined loading. So let's take a look at our problem statement today, right? We are going to be designing a sawn lumber header that supports gravity and axial loads, right? So this is how we get our beam column action. The length of the member is 8 feet. We have a Douglas fir larch species type. We have a 4x member, and we're going to be figuring out what depth we need to resist this loading. And we have a dead load of 50 pounds per foot, a live load of 75 pounds per foot, and then a pretty large seismic axial load of 4,750 pounds, and we'll be using ASD. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, I've got CalcBook open now, so we go and click into our NDS 2018, go over and click into our member design. And right, for a beam column, we need axial, we need flexure. We could check shear, but we're going to leave that one out for right now. We're just going to focus on axial and flexure design. Okay, so we can go ahead and start entering in our information here. So we need a visually graded lumber. We are going to go with Douglas fir larch. We didn't specify which grade, but we'll go with number 2. That's pretty standard middle of the road approach there. And we're going to start with a 4x8, and we'll see where that gets us. So we also want to switch over to our ASD loading. And you'll notice too that CalcBook automatically opens up the combined loading tab when it recognizes there's both axial and flexure design there. So no need to do that on your own. So we got our load duration factor. Since we are going to be using seismic and we expect it to be controlled by seismic, we can go ahead and increase this to 1.6. So we can go and take advantage of our load duration factor. No moisture content issues, no temperature condition issues. It's not incised, and it is not a repetitive member. It's just going to be a singular header. So we'll leave that there. Now we can go over and jump to our beam loading tab. Right, our beam is going to be 8 feet long. The shear analysis doesn't really matter. We'll leave it at 0. We're going to evaluate the moment at the mid-span. And then we can start entering in our applied loads. So our dead load is going to be a uniform load, and that's going to be of 50 pounds per foot. And then we're going to go ahead and enter in our live load. And that's going to be 75 pounds per foot. And we can take a look at our different diagrams here for our shear and flexure and deflection, right? Pretty straightforward there. We can jump over to our deflection tab, and I think everything here can stay as is. Our K sub CR, our modification factor for creep, I believe stays as a 1.5 since we have a seasoned lumber or dry lumber. Jump over to our axial design so we can enter in our loads and capacities for that. So we are compression, right? We've got an unbraced length of 96 inches. So that's right, that's 8 feet. And then we can go ahead and enter in our demand, right, which is going to be for our seismic load, and that is going to be 4.75 kips. And then we'll go ahead and jump over to our flexure design tab. And we need to update our bracing condition. And we're just going to say that this is 24 inches. Maybe we have some joist or trusses landing on the top of this beam at a spacing of 24 inches. So we'll use that for our assumed braced, unbraced length. Okay, so we've got our Flexure Design, we've got our Axial Design, right? You can see it's got the load case 9, dead plus 0.525E plus 0.75L, right? That's going to be our controlling load combination for this. And we can take a look at each of these calculations, right, individually, but let's first check out the combined loading calculation, because that's sort of what's driving all of this. So our combined loading calculation, right, is a little more complex than maybe your AISC calculation. There's a couple extra terms that get brought over from each of the individual calculations and then combined in a certain way depending on which equation you fall into. So since we're in compression, we're using section 3.9.2, and there's no weak axis bending here, so this term just goes to 0. Right, we bring in all of our different values from the equations, right? So we have buckling about each axis, which we need to bring over, so that gets brought over into this equation as well. And then obviously our axial compressive strength, and then our flexural strength about the strong axis, that gets all brought over as well and combined into this. So 0.22, pretty low, right? This is a pretty lightly loaded member in bending, so pretty low DCR value here. We can go back to our axial design, right? We can take a look at the individual calculation, right? Look at our adjustment factors. So we have that CD of 1.6, right? Everything else is 1. We do have a size factor adjustment there, so we get a 1.05 size factor adjustment, right? We calculate our column stability factor just like normal, and we calculate our design compressive strength from that. And then same thing for Flexure Design, right? We can go over and investigate the specific calculations for that as well. So similar thing, right? We have our adjustment factors, load duration of 1.6, right? The size factor for bending is 1.3. And then we do calculate our beam stability factor based on that 24-inch unbraced length, right? Which just comes out to be 1 anyways. And then we can get our design bending strength based on that information. So remember that combined loading, right? That drives all the load combinations for the other individual calculations so that everything matches. So it looks like our design works here. We could optimize a little bit, maybe 4x6, but a 4x8 seems like an appropriate size for an 8-foot span header. So we'll go ahead and leave that as is. That is a beam column design in CalcBook. We hope you enjoyed the video. If you have questions or suggestions for other videos or other calculations you want to see in CalcBook, please let us know in the comments below, and we'll see you next time.